Dear physics aspirants, right now I have the nuclear force subtopic of nuclei, and figure 13.2 will provide you the information regarding the potential energy of a pair of nucleus as a function of their separation. For separation greater than F R0 and the force is attractive, and for separation less R0 and the force is the strongly repulsive. Attractive and repulsive you will see here, and nuclear force will be discussed right now. It will provide you the better understanding regarding the repulsive and attractive forces. This time I have the nuclear forces, the force that determines the motion of atomic electrons as the familiar Coulomb force. What force? Coulomb force. In section 13.4 we have seen that that for average mass nuclei, the binding energy per nucleon is approximately 8 MeV, electron volt, which is much larger than the binding energy in atoms. Therefore, to bind a nucleus together, there must be a strong attractive force of a totally different kind. It must be strong enough to overcome the repulsion between the positively charged protons and to bind both protons and neutrons into the tiny nuclear volume. We have already seen uh, that the constancy of binding energy per nucleon can be understood in terms of its short range. Many features of the nuclear binding force are summarized below. These are obtained from a variety of experiments carried out during 1930 to 1950. The nuclear force is much stronger than the Coulomb force, so most stronger from the Coulomb force, acting between charges on the gravitational forces between masses. The nuclear binding force has to dominate over the Coulomb repulsive force between protons inside the nucleus. This happens only because the nuclear force is much stronger than the Coulomb force. So nuclear force is much stronger from the Coulomb force. The gravitational force is much weaker than even Coulomb force. So the gravitational is less than Coulomb, and Coulomb is less than what why nucleus for nuclear as a nuclear force. The nuclear force between two nucleons falls rapidly to zero as their distance is more than a few femtometers. This leads to saturation of forces in a medium of a large sized nucleus, which is region for constancy of the binding energy per nucleon. This is the region. A rough plot of the potential energy between two nucleons as function of distance is shown in figure 13.2 will provide you the information better regarding this. Two nucleons as a function of distance shown in the figure 13.2. The potential energy is minimum at a distance r0 of about 0.8 fm. This means that the force is attractive from the distances larger than 0.8 fm femtometers, and repulsive if they are separated by the distances less than 0.8 fm. Fm stands for femtometers. What? Femtometers. The nuclear force between neutrons Neutron, neutron, proton, neutron, and proton. Proton is approximately the same. The nuclear force does not depend on the electric charge. Unlike Coulomb's law or the Newton's law of gravitation, there is no simple mathematical form of the nuclear force. So aspirants, when you study the nuclei, then nuclear force will be very important, will be understood when you study the nuclear force in terms of the gravitational force and the Coulomb force, and what is mean by the repulsive and the attractive forces. We will meet in next discussion with lot more related to the nuclei chapter. Till then, thank you for very much. Thanks for watching the video.